Okay, in this video we're going to talk about the first of our scheduling algorithms in this course, and the simplest one, first come, first serve, usually abbreviated as FCFS. So you should remember the idea of the instruction cycle, so the fetch execute cycle. You should have a vague idea of the fact that we can stop a process by interrupting it and then resume it later. You should have a notion of the memory hierarchy and this idea of caching, I/O techniques, and multiprocessor and multi-core architecture. And you should also have an idea of what the difference is between the term process and thread. So before we start discussing a particular scheduling algorithms, it's a good idea to get a grasp of the main aspects of scheduling algorithms in general. So typically when we discuss them, we'll talk about two main aspects. First, there's the selection function. So that is how does the scheduling algorithm decide, when it has the chance to decide, which of the currently ready processes should be run next. So given a queue, which we call the ready queue, of processes, which of these should be selected for running next? And the second key aspect is the decision mode, which is basically when it decides it should be selecting a function. It should be using this selection function. So we already know that typically processes will often I/O block themselves or end up blocked for some reason. But we can also have a scheduling algorithm that uses some method to decide to stop the currently running process and start another one. And we group these into two main categories. We group scheduling algorithms into two main categories with this. They are the non-preemptive scheduling algorithms. These will not interrupt a running process. They simply, once a process has been started, they allow it to continue until it either finishes or blocks itself, for example, with an I/O call. Or in the other camp, we have the preemptive methods. So these will, at certain points in time, decide to interrupt currently running processes and schedule a new process using the selection function. And in this case, the preemptive ones can be broken up into some smaller subcategories, but we won't discuss that in this video. We should also discuss some important terms that we'll be using a lot when we're discussing and comparing scheduling algorithms. So four of these important values are all times. There is the arrival time, which is the point at which the process enters the system. So when the process is put into being ready to be executed. There is the service time, which is the amount of time the process actually needs itself. So how many CPU cycles or whatever time metric you want to use, but how much time that process actually needs on the CPU. There is the turnaround time, which is how long the process spends in the system. So it is the difference between the arrival time and another time, the finishing time, which we haven't got a particular value referencing here, but whenever the process finishes, the difference between then and when it arrived is its turnaround time. And then we also talk about the normalized turnaround time, which is simply the ratio of the turnaround time to the service time. So for example, if we have a process that requires 50 time units to run, but the process arrives at time unit 2 and leaves at time unit 100, then we know that the turnaround time was 88, and so the normalized turnaround time is 88 on 50. So this can be a useful method for comparing, because if a really, really long process experiences a short overhead delay, that's not nearly as significant as when a much shorter process receives that same delay. So a 5-minute process that experiences a 1 second delay, there is not a huge problem, but a 1 millisecond process that experiences a 1 second delay can be a much bigger problem. So now that we have those terms defined, we can actually go ahead and firstly define first come, first serve, and then later discuss it with reference to a specific example. So first come, first serve, also known as first in, first out, or a strict queuing scheme, is the simplest scheduling policy we can come up with. We use it as a baseline to compare other methods. The selection function for first come first serve is simply whichever process has been in the ready queue the longest. So whichever process it's been the longest since we popped it in the ready queue, that's the one that we run next. The decision mode is non-preemptive, so it doesn't do anything clever to try and decide to interrupt currently running processes. Simply, when we have to find a new process to run because either the current process has finished or the current process has blocked itself with, say, an IO call, then we will use the selection function, which is again a very simple selection function. We can implement it very easy just by using the ready queue as a normal FIFO queue. So we don't need any fancy priority queue scheme or anything like that. It's very simple to implement. But what we will see is that we won't see it in this example, but we will see it in future examples, is that it tends to favor CPU-bound processes over IO-bound ones, which we do know is a problem, but it does have the advantage in that it is very simple. So better than me spending a long time describing first come first serve, let's just step straight into an example. Let's imagine a situation in which we have 4 processes, each of which arrive one time step after the other in a simple scenario, and we're not concerned about any sort of IO blocking or anything like that. These are simply processes that just have some CPU time that they need. So process A, which we'll denote as purple, arrives at time 0. Process B arrives one time unit later at time 1, process C at time 2, and process D at time 3. Now one thing we note is that these processes have very different service times. So process A only requires 1 time unit of service time, and the same for process D, but process B and C are both very long running processes, both of which require 100 time units each to run. So we will also refer to our ready queue here, and I will start discussing in time steps as we go along. So at time step 0, process A arrives and is the only process in the ready queue, so even if we had any form of scheduling algorithm, it would always choose to run process A at this point. So process A runs for 1 time unit, during which nothing happens, and then process A actually finishes at that point. So process A is done and it goes out the window. Nice and simple. But now we are at time step 1, and so process B enters the system. Again, we don't have any more processes to enter the system, so we start executing process B, and nothing else happens until time step 2, when process C now enters the system. So process B is out of the ready queue because we're actually running it, and process C now enters the system. However, we know that first come first serve is non-preemptive, and because B is not IO blocking it, we continue running process B, and process C just sits idle in the ready queue. At time step 3, process D enters the ready queue, but again, because we have a non-preemptive policy, process B will continue to process up until it gives itself up, which is actually 100 time units after this. So this will be at time step, will be 100 time steps after process B started, which is actually 101. At this point, the process B finishes and leaves the system, so now we have a time for our selection function to be used. And remember, the selection function simply picks the process that has been in the ready queue the longest, so whichever process is at the front of the ready queue. So this time it picks process C, which begins executing here at time step 101. Now, again, because this is non-preemptive, process C will continue running for its 100 time steps and finish at time step 201, because it requires 100 time units as well. So it has left the ready queue that whole time. And then at this point, when it relinquishes control, we can finally run process D, which only requires 1 time unit, over here and terminate finally at 202. And our ready queue is empty. So using this, we can now start to fill in this table of important time values. So process A arrived at time step 0 and started at time step 0, and it finished at time step 1. So its turnaround time was 1, which means its normalized turnaround time, the ratio between the turnaround time and its service time, is a perfect 1. So that's actually the best value we could have. So as far as process A is concerned, we're chuffed and very happy. Process B arrived at time 1 and immediately began executing because process A had stopped. So it starts at time 1 and it finished at 101. So we again had a perfect ratio of turnaround time to service time of 1. Process C, not so great. It entered the system at time 2, but it couldn't begin until time 101 when process B had finished. So its start time was 101, its finish time was 201, so its turnaround time was 199, giving us a pretty terrible normalized turnaround time of 1.99, so almost 2. So it actually took almost twice as long to run process C as it needed to as far as the original dispatching was concerned. Now finally we get to process D, for which we have the worst news. Process D arrived at time 3, but it doesn't begin processing until process C is finished at time step 201. Then it processes for a whopping 1 time step, so finishing at 202. So its turnaround time, 202 minus 3, is again 199. This time giving it a very terrible normalized turnaround time of 199. So almost 200 times as long as the process actually needed to run was how long it took from when it entered the system to when it finally finished. And we can see immediately where the first come first serve has failed in this case, because if it was somehow magically known how long this process would take, then the decision at this point here, where we had both C and D in the ready queue, should clearly have said, let's favour the short process, because we can finish that quickly, over the long process, for which a small delay is not so much of a problem. And we can also see that the lack of preemption means that no matter what, because process B entered the system, entered and started running before C and D arrived, there was nothing that could be done with a non-preemptive method to let D do a small amount of processing in order to have a better averaged normalized turnaround time. Because we can see quite a big discrepancy between the experience that some of the processes had simply by the order in which they arrived. And that is one of the big problems with first come first serve. But we can also see that the actual implementation and understanding of it was very simple. Simply pop off, run a process, wait until it finishes, and then pop off the next process at the front of the ready queue. So we've covered some of the basic scheduling algorithm components. So remember we sort of broke it down into 2 rough categories. The selection function, which was which process do we choose to run next, and the decision mode, which was at this point all we're concerned about is whether it is preemptive or non-preemptive. We'll discuss further in the lectures. And we also went through one example of first come first served, seeing how it works, and also some of the drawbacks of it, but we also should remember that the simplicity of this method can actually be a strong benefit. In some cases where there is no benefit to be achieved by clever scheduling, something simple like first come first serve can actually end up with much reduced overhead, because the selection function is very simple and there's not a lot of pointless interrupting and context switching which can introduce extra overhead. So just because it's simple and we can point out some obvious flaws doesn't mean we should completely ignore it as a potential algorithm.